This report, lots of technical stuff, correct? Lots of what's happening, and also, you know, what Hollywood thinks, what the public thinks. But we all do realize that what it needs most is us, humans. Because, you know, technology is great, but we're going to send humans, not robots this time. Humans, us. Now, I would like to talk to you about what we are going to name our rocket. Because, you know, I'm Artemis. Officially, Artemis is the goddess of the... That's fine by me. That's totally fine by me. And no, I don't need to have my name on that rocket that goes to Mars. That's, you know, not me. But, you know, if we think about it, getting humans to Mars on the Ares rocket to Mars, so we're sending the god of war to the god of war. Also, again, we're sending a male. Shouldn't we be more inclusive? And if I look at the audience, I'm very, very happy to see there are lots more females every year to our Humans to Mars Summit. Especially today, I see really a large contingent of females all around the audience. Great, because we humans, and that's males and females, are going there. But like I said, Ares rocket to Mars, I propose that we send the lover of Mars to Mars, mighty Aphrodite. I think the rocket should be named Aphrodite. Now, I have the great pleasure, I see the chairs are there, so then I can now proceed to introduce to you Mark Kaplan. Kaplan loves hosting and producing Planetary radio for the Planetary Society. He was just 17, that's some time ago, when he got his first job in broadcasting, and since 2002, he combines his love of space with his love frequently serves as moderator at space events, in which capacity he serves us here. Mark is passionate, very passionate, about the importance of space exploration and the exploration of Mars, and as such, I expect him to keep the discussion going in his panel of NASA space exploration leaders. Please come to the floor.
Sure. Thank you, Artemis. I'm going to grab my seat. Good morning. We have a great panel for you. Are you putting those?
Yeah, I'm not sure it works, but it'll be great.
I'll try not to trip over them.
Oh, that's nice.
And you've already heard who I am. I've always loved the name Mark, but it's Matt, as it
Yes,
says.
I noticed. Sorry about that.
We've got some terrific people lined up for you today. And for those of you who are watching us online, we hope that you're also enjoying the program and that you'll be sticking with us over the next 3 days, or 2.5 to be more precise. And we will even have some content for you during the breaks in the program here, so that the people here in person can take care of other business. I'm going to get started right away because we have an awful lot to pack in to a very short time period. And to do that, I'm going to bring out the first of our 3 outstanding panelists, and that is Steve Jurczyk, who serves as Associate Administrator of the Space Technology Mission Directorate at NASA headquarters. He's Director of the agency's Langley Research Center, a position he moved up to from Deputy Director in 2014. Almost got it right. Musical chairs. Have you seen the spectacular test of the Orion launch abort system? I can't see hands, it's too bright up here. But if you haven't looked at that, you really ought to take a look. It's very exciting. That was one of Steve's many efforts as Director of Systems Engineering and later Director of Research and Technology while he was at Langley. Now he manages and executes NASA's space technology programs, focusing on answering the agency's exploration and science mission needs, working with the greater aerospace community, and developing the nation's innovation economy. Got any fans of the annual NASA spin-off book here? I love it. I get it every year and often talk to those people. That's also part of Steve's bailiwick now. He's a recipient of the NASA Outstanding Leadership Medal and the Presidential Rank Award of Meritorious Executive. Please help me welcome Steve Jurczyk.
Thanks, Matt.
Thank you. Next up is Jim Free. Jim Well, Steve isn't the only former center director on the stage. Jim Free had been director of NASA's Glenn Research Center for 3 years until he was snatched up by headquarters just a couple of months ago. Now he's deputy director of the Human Exploration and Operations Mission Directorate. He joined the agency in 1990 as a propulsion engineer, and then he moved to Glenn for work on the ISS. That was interrupted for a year at JSC, when he was the Orion Test and Verification Manager, then back to Glenn in a variety of positions. He was deputy director there till he moved into the big office. And your deputy at Glenn, who you got to select, astronaut Janet Kavandi, I hope I got her name right, just moved into your former seat. So she's moved up into director. He is the recipient of a NASA Outstanding Leadership Medal and a NASA Exceptional Service Medal and numerous other awards. Please welcome Jim Free. Thank you. Finally, we're going to introduce Rick Davis. Rick M. Davis, another NASA HQ guy. He's the Assistant Director for Science and Exploration in the Science Mission Directorate. He's a bridge between that science-devoted side of the agency and the Human and Exploration Operations Mission Directorate. An example of that collaboration between these groups is his co-leadership of the study that is currently underway that is beginning to identify the potential landing sites on Mars for humans. Anybody who's still sleepy out there ought to be wide awake now. I think that is incredibly exciting. Rick came to DC from the Johnson Space Center, had several positions there. I got to think the coolest was serving as lead Capcom. You know, the guys who get to talk to the people up there. He did that as lead for ISS Expedition 13 and STS-119. He also oversaw coordination with the international ISS partners, including crew training and psychological support. That was after he returned from Russia. He lived in Russia at Star City for 3 years, working for NASA as a liaison there. And he started as the trainer of several space shuttle crews. Among his awards are NASA's Exceptional Service and Exceptional Achievement Awards. So please welcome Rick. All right, gentlemen, we're going to forego opening statements, and I still don't think we're going to cover all the terrific topics that we've got laid out for us today. And some of these have already been touched on by the great speakers who've come before us. But let's start with this overview, and that is, are we on the many converging paths that are going to get humans to Mars in the 2030s? Steve, would you like to start?
Sure. So yeah, we, as was described before, we have quite a few challenges to get humans on Mars. We have to evolve capabilities that we have now, like environment control and life support systems and in-space propulsion systems. And then we have to develop entirely new capabilities, like those needed for in-situ resource utilization and surface power to support those systems and other systems on the surface of Mars. So yeah, we know that we still have several architectural options, and we continue to trade those options. But we know, regardless of what the architecture ends up being, you know, and we're a decade or more from deciding on all the details of that architecture, we know that there are certain capabilities and certain technologies that are required to enable those architectures. Like I said, evolving some capabilities and creating whole new ones. Dava mentioned the entry, descent, and landing challenge. That's when she responded to the Red Dragon question. That's a very large challenge. Right now, we still essentially use the Viking technology with respect to the vehicle planform and the supersonic parachute technology to get from about, I don't know, 15,000 miles an hour to 0 in 7 minutes. Through a very thin atmosphere. We can land 1 metric ton right now, and we're going to have to land probably 18 to 23 for the ascent vehicle to get crew off the surface and back to the Earth. So we're just one of many challenges, but we know we know regardless of architecture and the details of how we're going to get there, we are working very hard to develop those capabilities and technologies using right now the International Space Station and ground-based testing, in-space testing with robotic spacecraft, Robotic missions to Mars, we're learning a tremendous amount, not scientifically and technologically. And then as we push out beyond low Earth orbit into cislunar space, there's a lot to be done there and proven there even before we move out and onto Mars. I'll stop there.
Jim, Rick?
Go ahead, Rick. So if you go to the next slide, that'd be great, if we could, please. So
There we go.
great, thank you. So we have actually, what's amazing to me, I actually came out of the human spaceflight world and now work in the science side of the house, and which has been a really exciting change for me. One of the things that's amazing is if you look at this chart, this is a list of all the missions that have gone to Mars. It fascinates me because the red ones up towards the top are all the ones that failed. And in fact, the United States is the only one that's actually made it to the surface. We hope to change that here shortly. And we work with our international partners as well as soon our commercial partners to actually make that possible because there is a tremendous amount to learn. I spent 12 years in an ISS flight control room, and I will tell you, if there was a mantra that we have in the flight control room, it's in space is dangerous, on the surface is safe. And sometimes I think we transpose that to Mars and we assume that in space is dangerous and on the surface is safe. I would actually say with everything we've learned across all these missions and with our current level of technology on the surface of Mars is dangerous for us. And we need to step our way and have and build up our understanding of what it takes to do that. What we've learned in the science side of the house executing these robotic missions is that we need a cadence of missions that actually, because you essentially are limited to these 26-month launch window opportunities, and so you don't get many opportunities to actually learn about Mars. And so the point being is that by doing a steady set of missions that are logically sequenced, that are building and ultimately building to humans being there, we can solve these problems and actually make tremendous headway. And yeah.
I love how that gets bluer and bluer. We're getting better at this. I also have to correct you because Jan Warner of ESA already yelled at me once when I said that they had never been landed on the surface. He said, "Oh yes, Beagle landed.
That's true.
It just didn't talk back to us."
Exactly. That's right. We do have orbiter imagery of Beagle on the surface. It just never talked back. Yeah, never come back. That's true.
But the moral of the story really is that Mars is hard. We should not take it for granted. But as Davis said, by working together, we can do this, and we just need to piece the pieces together.
All right, so the good news is coming. We've also heard already about some of the essential technologies in various areas that are underway right now. Let's start with SLS Orion. Things moving forward.
Absolutely, they are. Let me just highlight real quick. The clicker's not working here. If I could get the next chart, just to finish a thought on the previous discussion.
Sure.
Dr. Newman talked about our journey to Mars. What we're doing now is breaking down that journey to Mars, breaking down into further phases with more granularity, objectives for each. The important thing is to remember that we're exploring Mars today, both with the rovers that we have, but also with the technology we're developing on ISS. We can't overlook the importance of ISS. Dr. Newman mentioned that. What we've taken now is all the phases in between there and come up with objectives for each. Objectives like in phase 0 on ISS. How do we do things with autonomous crew? In phase 1, where we have these defined decision gates at the end, we're trying to develop some more autonomous rendezvous and proximity operations, which will be demonstrated on ARM. And then phase 3, further exploration and validation of the ECLIS systems. So we're heading in that direction and building, Matt, off of what you asked. Next chart, please. What's the progress that we have going on right now?
Flip a couple ahead.
One more, please.
One more slide.
That's two.
So you get to the Orion. 2 more then, please.
2 more, yep.
Sorry, the clicker's not working here. Not going.
I don't know if they caught it. Can we advance 2 more slides?
There you go.
There we go.
So what's going on in Orion today? This is the EM1, Exploration Mission 1 crew module at the Kennedy Space Center shortly after it was delivered last year. It's undergoing outfitting now, first of some of the essential structure that was used to validate the proof pressure test, which was done just 2 weeks ago, where we went to 1.25 times the operating pressure. We're now adding secondary structure to the vehicle, some 500 plus pieces of secondary structure to the vehicle. So well on its way to the 2018 EM1 mission. In parallel, we're working on the service module. We talk international. That's being developed by the Europeans. Actually, I'm going to Germany later today to have an event with the Europeans to celebrate delivery of the structural hardware for the EM1 service module. If you go to the next slide, please. On SLS, go one more. I think the next one's a movie. On SLS, we're developing the tanks. They're being developed at Michoud in Louisiana, where the oxygen and hydrogen tanks are being assembled using in this incredible tooling. I mean, the tooling itself is an engineering marvel with friction stir welding. So we have the hardware in development. Again, the theme is we're developing the hardware going to Mars. Next, please. We have our engine testing underway at Stennis Space Center, testing the RS-25, the former shuttle engine. One more, I think, is a movie. Expanding the envelope for this engine, using it well beyond what was ever intended for the space shuttle, operating at 109% thrust level, all new controllers. Eventually, it'll operate at 111% of its original operating parameters. Next, please. And at the Kennedy Space Center in the Vehicle Assembly Building, you can actually see the outline of half of the SLS there. You can see the solid rocket motor outline in the platform with the core stage outline. The platforms are going into the VAB for this massive vehicle. Next chart, please. And we're also working on the hardware that will ride out to the pad on the mobile launch platform, where all the systems go into the platform itself. At the bottom there, you think it's just a piece of structure holding it up. The systems in there for software, for air, for propellants are just incredible. And then, of course, they all have to run up to the towers across umbilicals. So that's my 1 minute on how are things going on SLS. Ryan, not a lot of progress.
There's a solid rocket booster test coming up? Or
There is, June 28th.
June 28th, okay.
Qualification motor, the second one in Utah.
And that tank assembly, where the tank was being welded, you talked about how innovative that is. It's done vertically.
It is, yes. So it's the segments go in and come out. It's almost like a Pez dispenser.
Let's keep going. We've already heard a little bit about developments in solar electric propulsion, and that really it's a question more of scale, since electric propulsion is coming on strong across the board for commercial payloads as well, commercial satellites. But what about nuclear thermal propulsion, the kind of stuff we saw in the movie The Martian that was driving that huge ship? They didn't make a big deal about it, but they do mention at one point that there was a nuclear reactor on that vehicle.
Yep. So first, talk a little bit about high-power solar electric propulsion. So Jim Zoll's center, now the Glenn Research Center, really did a great job in developing two critical technologies for high-power solar electric propulsion. One are large area solar arrays to provide the energy and power to drive the engines, and those were with two industry partners. DSS developed the rollout solar array concept, and Orbital ATA developed their kind of fanful megaflex concept, and those were developed very successful ground demonstration units and tested. And actually, they've started to be commercialized in the commercial communication satellites where they need higher powers. The other technology was the higher power Hall thrusters, magnetically shielded to improve lifetime, 12.5 kilowatt thrusters. And we're actually for the asteroid redirect robotic mission. So lots of good progress there. Now to get to actually answer your question, nuclear thermal, we have been working nuclear thermal propulsion technology at a low level for years. This year, Space Technology Mission Director at NASA is picking it up in our game-changing development program. And we're focused right now on developing the fuel for a reactor for a nuclear thermal propulsion system. And so we'd like to move from highly enriched uranium fuel to low enriched uranium fuel. We think it'll be, we have processes that'll lower the cost of producing it and reduce the infrastructure. And we also believe it'll be less costly in the end with respect to handling and security. So very fundamental low technology readiness level work in low enriched uranium fuel for the reactor. We're also going to do in-house and with industry system studies to look at what would a nuclear thermal propulsion system architecture look like using a reactor based on how the progress goes, in which case, if we're successful, we'll then roll into more of a a reactor/engine development activity for a ground demonstration. But the motivation for doing that is to reduce trip time for crew. That is the motivation. There are many human health and performance challenges with now 18-month mission durations given the current chemical and propulsion technology. And so we're really looking at advancing what we call rapid transit technologies like nuclear thermal propulsion to reduce trip time for crew.
I know NASA's been working pretty closely with Franklin Chang Diaz, the Ad Astra folks, on that variation of what will end up being nuclear propulsion, and I assume that's moving forward too?
Actually, that's what I call very high power electric propulsion, right? The VASMIR and other technologies, which are 100 kilowatt type systems versus the 12.5 that we have now. And they are also lower TRL than the Hall thruster technology. But we are also, that's actually through Human Exploration and Operations Mission Director, Advanced Exploration Systems, looking at advancing the very high power electric propulsion technology as another rapid transit capability and approach, yep.
Down the line, way down the line.
Yeah, again, it's kind of in the very low TRLs right now, although could be advancing fairly rapidly with a successful long duration ground demonstration test.
Rick?
And I just would, as a sort of an end user of the technologies that they're developing in Steve's directorate, I would say that solar electric is something very exciting for us because I'll give you an example. We are exploring an option for an orbiter around Mars. The current MRO has been an amazing bird. It's 10 years old and it's past its design lifetime, so we're trying to figure out what we need. And the big thing that's screaming right now, really from a perspective of human spaceflight combining with science, is a new reconnaissance bird that actually can find water. And what's really neat is that with solar electric, you have a very efficient way of getting that bird out there. It can be bigger than what we've done previously, which means, even more importantly, when the satellite arrives at Mars, it has abundant power that we have always been short of in the Mars exploration program because we're not using it for thrusters anymore. And so what we can do is take that power, redirect it to a radar system potentially, and really find out where the near-surface water deposits, which we know are significant on Mars, but we haven't been able to get the right radars there previously. So here's a case where technology is relatively near term that's being developed by STMD is actually really enabling some very exciting missions that really were not possible previously. And so we've learned that, taking baby steps, you want to do the far out investments too, but also bringing them in and actually using them as soon as you can is the way you also learn. And we're very thrilled about this.
I want to mention just in passing, there was a contract just awarded to one of our sponsors here today, Aerojet Rocketdyne, for development of advanced solar electric propulsion, right?
Correct. Those would be the development of the 12.5 kilowatt thrusters and the drive electronics for the asteroid redirect robotic mission hardware. Yep.
Let's quickly talk about getting down to the surface. You said, and this is better than I thought, up to, you said 18 to 23 tons?
3, yes.
Yeah, okay. Well, that better than 30 tons, I suppose.
It used to be 30. We're refining the architecture and applying new technologies and getting it, the range right now is 18 to 23, yep.
Well, I'm told, I think Adam Stelzer, Rick Manning, two of the guys who know how to get stuff down to the surface, who are trying to figure this out right now, are out there in the audience someplace. Are we looking good? Are we going to figure this out?
Are we looking good? So that's kind of a loaded question, but so we are developing a suite of technologies to try to land larger masses on the surface of Mars. So first, kind of the first step would be a robotic Mars round trip mission. And oh, by the way, while we're going round trip, we might as well bring some samples back. So that's in collaboration with the
Scientists would like that.
Yeah, Science Mission Directorate, right, the Mars Sample Return Mission. And we're looking at the ascent vehicle for that mission, depending on how much sample we want to bring back, of 3 to 5 metric tons. So that's getting from 1 to 3 to 5, and that would be a challenge, but something we can do in the nearer term. So there's several ways we can do that. One is a better aerodynamic drag device, and that could be a larger and more effective supersonic parachute. It also could be an inflatable that we use at supersonic speeds that we successfully demonstrated on the low-density supersonic decelerator project. So that was the good news on LDSD. We demonstrated the inflatable twice in a high-altitude test flight. The not-so-good news was the supersonic parachute failed twice, structurally failed twice. So there's a lot of work to do in understanding the deployment dynamics of supersonic parachutes, including modeling of very chaotic, turbulent flows and the interaction of those flows with a very flexible structure. So we've got some work to do there in both modeling and simulation and physical understanding of that. But we're going to continue to do that and understand that better and figure out if designing a supersonic parachute is feasible with a better drag performance than the disc gap band parachute that we use now. Also, there's supersonic retropropulsion, which is an alternative to decelerate from supersonic speeds down to subsonic speeds. And actually, the first tests, hopefully, the first test of supersonic retropropulsion on Mars will be through our collaboration with SpaceX on Red Dragon. And the Red Dragon's going to be on the 5 to 6 metric ton scale, uncrewed vehicle, and their plan is to slow down from supersonic speeds all the way down to the surface using retropropulsion. And so for NASA, it's an entry, ascent, and landing technology demonstration opportunity, and that was our prime motivation, one of our prime motivations for collaborating with SpaceX on that. And then there's terminal descent and landing technology, and we decided to fly terrain relative navigation on the Mars 2020 mission. And so using imagery and 3D elevation maps, we can do hazard avoidance in real time. And that actually is interesting because it opens up some landing sites that are scientifically interesting, but would be too dangerous to land on due to rocks and slopes. But now we can't, with the terrain relative navigation, we could land on that. And so precision landing and autonomous landing and hazard avoidance is also an enabler for EDL. So lots of challenges there, but we've got a lot of tech development going on to try to develop the technologies to first enable a Mars sample return mission and then eventually the human missions to Mars.
If I might too, I was glad that Rob and Adam are both here because they've been they and their teams have been the gurus for getting into Mars. But really, this is a tri-directorate thing, and Steve's guys are heading it up. But the bottom line is it's about getting all the right smart people together. This nut can be cracked, and they're making substantial headway. And it's really kind of exciting to see this evolve and to enable the types of things that Steve just described.
Did I say Rick Manning before? I think I did.
It's Rob.
Yeah, it's Rob, of course. Many times. Sorry, Rob. He's out there. Very quickly, life support. It's also come up today. We haven't achieved yet anything like what's going to be necessary to send these people out with no resupply for the 2 or 3 years that they're going to be making that round trip. How is that coming along?
So that's where I get back to what we're doing on ISS today, right? We have goals that are set for what we think we need around Mars and hopefully get a chance to talk about architecture, but those are going to drive the architecture, and we're trying to prove those systems out today. Oxygen recovery as an example, 42, 47% on ISS today. We're trying to get to 75% for these long duration missions. The place to test that out is on ISS. We're doing that today through some of the systems we're sending up, through what we have planned to do in the near term, where we're going to dedicate 4 racks on ISS to advanced ECLSS systems. That's the criticality of getting ISS, the extension, which we have the 2024, and getting systems built and up there. And life support also goes into fire safety. Right, fire safety is another element of life support that we're testing today. We have an experiment, and I'll be my Glenn's Research Center homer here for a second. I still have center blood running through me. We're doing a large-scale fire experiment on Cygnus when it departs. June 14th, we're going to light a
Such a cool
fire.
experiment.
It's great. But that we're using low Earth orbit today to test those systems out that we're going to need for Mars, and our goals are what we need at Mars. So it's not just haphazard, how are we picking, it's what we need out at Mars.
Yeah, and so, on station, 8 years is going to go by really fast. And we were at a point now with the 50% of the experiment time that CASIS has to offer to commercial, researchers and technologists, and the 50% that NASA has. We are more than oversubscribed with crew time available to do the experimentation. And so we are really going to have to prioritize, particularly on the NASA side, what are the critical things to get done on station before 2024, and we move out into cislunar space. And obviously, advancing life support technology is really critical. We got to get the efficiency way up. I'm not sure we have to completely close the loop, but that would be ideal, but we got to get the efficiency way up. And we've got to get the reliability way up, because if you're involved in station at all, you know how things kind of in general, but on the life support system side, kind of break down regularly, and we definitely have to get the reliability up. So yeah, Jim mentioned oxygen recovery and CO2 scrubbing. Also, we developed and delivered rapid cycle amine technology for better, more efficient CO2 scrubbing, and we're also looking at advanced technologies for the portable life support system for the future, EVA suits and surface suits. And so we developed things like variable oxygen regulators and better scrubbing technology for the PLIS, for the portable life support system. So that is really critical. And then we're looking at even more advanced and more kind of far out concepts which couple environmental control and life support and ISRU, say food production, plant growth that also could provide not only food but also CO2 absorption and oxygen generation, right? We call those bioregenerative systems. And so we're looking at investing in research, lower TRL level research and technology development and things like bioregenerative systems, where you're trying to kind of create a mini ecosystem.
So ISRU, in situ resource utilization.
Can I come back to that theme, though? In my sort of opening comments, I talked about how hard Mars is, but part of that, it's hard because we don't know it and we don't build it into our architecture as much as maybe we need to. And so the interesting thing about ECLIS for me personally is that, you mentioned 1,000 days or 3 years. Well, reality is we're probably going to pre-position supplies and logistics in a Mars parking orbit. So really, you're not talking 3 years. You're talking a much smaller amount of time that actually does start to approximate what we've learned on ISS. And so building that into the whole equation and potentially even pre-positioning on the surface of the planet, that really offloads what the technologies need to be there. I was actually in the ISS flight control when we put the urine processing assembly on board, which was not ready for prime time, I might add, at the time. But the point being is we got through it, we got the parts on there, and if you have that logistics supply chain in place, you can make really amazing things happen.
Yep.
Our time is flying by even faster than I thought. Let me ask you, and then I want to come back to that ISRU for a second. Habitation modules. Nobody's going to want to live in Orion for 3 years. How are we coming along? Is it a step in the right direction? We've seen the Bigelow module just attached to ISS.
Right. So habitation, again, we look at ECLIS, habitation all being tied together. Beam is on ISS, be inflated on the 26th, as I recall, of this month. A great step at understanding the challenges and benefits of inflatable modules. Our next step, broad area announcement on habitation just went out phase 2. We're doing phase 1 with a number of companies right now, looking for those innovative ideas on how to do habitation. Our international partners want to play in habitation. When we talk about the architecture, the elements we have to develop are multi-destination capable. We need a habitation, as you say. If I got to go to space, I would probably live in Orion for 3 days.
Yes.
That's me. But we do need that habitation space for some of these systems we have to take and give the crew resources, place to do science on their way, a place to stage EVAs from to do further work. So those multiple elements of how we're developing HAB right now, I think, are leading us to what is our next step. And then that feeds into the architecture. What kind of HAB do we need? Do we want to design a HAB for cislunar and then another one for deep space? Probably not an affordable path to do both. We might have to find a compromise in there to do a modular HAB. So I think it's important to point out that we're looking at multiple paths to do that, and that international piece, of course, plays into it. Just one more comment on Rick's statement on the urine processor. Some of the ECLIS systems for ISS were tested on the ground for 5 years, and they went to orbit and gummed up right away. That tells us we can't afford to do that again. We have to get those systems up into microgravity as soon as possible and understand those right away. So you'll see that while we'll do some ground development, our focus is getting things on ISS.
Back to in situ, living off the land. We're not going to be able to bring, to import potato fertilizer the way Mark Watney did.
Yep. If Mark had a little bit of ISR technology, you wouldn't have to MacGyver it, I say, as much as he did, because he was like MacGyver up there. So yeah, it's critical. If we're going to do human exploration of the solar system safely and affordably, I think ISRU is a critical capability that we need, and we need to develop technologies. And it's one of the new capabilities that we need to develop that we haven't had needed in the past. So it's everything from producing fuel on the surface to building materials. David talked a little bit about 3D printing to growing food, right? And so we're starting with a demonstration of ISRU on Mars 2020 called MOXIE. And let's go advance a few slides. We actually have an ISRU slide. Let's see if you could advance. Next, keep going. Yep, here it is. So you see MOXIE in the upper right-hand corner. It's on the rover for 2020, and it's going to produce oxygen from atmospheric CO2. So we're going to kind of demonstrate that it can be done at very small scale in a relatively small package. And that's one way to generate oxygen, but also there's quite a bit of water on Mars, right? And if we can extract it and get it out of the surface, get out of the soil, that provides another opportunity not only for water, but for hydrogen and oxygen.
So I would say, to build on Steve's comment, that's actually one of the exciting things we've learned in the recent past, is that there are significant quantities of water on Mars. And I actually once upon a time was a history major, and I will tell you, if you look at the human exploration, the humans are generally going to where there's water. And
follow the water.
Follow the water.
Said, yeah.
And I think the same thing will happen on Mars. And the good news is now we know there's significant amounts of water. There are old oceans that are essentially covered with a very thin layer of regolith on top of them. There's glaciers, we know this now. We know that there's minerals that could potentially be harvested for water, and so there's a whole range of these things. And so there's two pieces that are really kind of fast breaking. We're beginning to realize that water may drive where the human landing site gets set up. There's a piece of recon that we need to do because the previous orbiters, like I said, did not have high power available to them, so we couldn't figure out. We answered a lot of really important science questions in terms of deep aquifers being available or not. But what we need to know is where the near surface water ice is, if you will, so that can be harvested. And in fact, that could even drive where we end up setting up as a semi-permanent base. And so very exciting things, new things. We're going to need a lot of new ideas to really flesh this out. And then once we find it, which we can largely do from on orbit, but then we'll have to ground truth it, and we'll have to have the technologies to actually extract it. I mean, you're talking in an atmosphere that's has an extremely low density, and there's some really and very cold. And so there's some really amazing challenges just figuring out how to do that. And so I would sort of see this as sort of the next area of essentially recon and tech development that needs to come up.
Yeah, a little bit more about 3D printing. We have several efforts going on, including a Centennial Challenge to use Martian regolith, not a lot of water, and not a lot of power, and trash, inorganic trash, plastics, for example, to 3D print the components and then assemble those components into a habitat. So we're leveraging the 3D printing technology there. And then food. We got a lot of work to do there. We've had some station experiments like veggie, and those will how do you grow food with not a lot of water that's volumetrically efficient and resource efficient, and also over time, given the space environment of microgravity and radiation, will that food maintain its nutritional value? Will actually provide nutrition for the crew? And so that's work that's being done on the ISS and will continue to be done on the ISS and on the ground. So like I said, everything from fuel, building materials, and to food. It's really important. Without that, the logistics train for humans to Mars is going to be just unaffordable, and architectures don't close. Jim is absolutely right. Depending on how much ISRU you assume you can do based on the technology and the capabilities, it enables or closes off different architectural options. And then Rick is absolutely right in that we are going to have these systems on the surface of Mars well ahead of crew. They have to be autonomous, they have to be reliable, and they have to produce the things that we're going to need to sustain crew on the surface and get them back off of in a way that we have high confidence in before we push off to Mars.
I hope we're giving everybody here, you guys probably already knew this, an even better idea of just how hard this is going to be to pull off in less than 20 years. On top of all of this, all of these converging technologies that are still in development, they all have to come together. They all have to be integrated. Is that happening as well?
I had mentioned earlier the architecture work going on, and a lot of people want to build architecture from left to right, right? Because I said the worst enemy to any design now is we can do CAD. So everybody believes, well, you did the CAD, it looks great, you can go there now. If you build it left to right, you may not be optimizing what you need at your end. If you build it right to left, you may never build an architecture that closes. So we're trying that integration piece, we're trying to do that in both directions. There's things we need, like Steve talked about in terms of landed mass. There's things we need in terms of systems. There's a gear ratio that what that takes to get it off the surface here on Earth, assemble it somewhere in some orbit, and push on. That's the trade that's happening in both directions right now. So the answer to your question, Matt, is the integration is happening. The architecture work is going on through our future capabilities team, some of our exploration architecture work that merges all three of our mission directorates into that process, so that we understand if we're going 47% to 75 and we get to 75, then this is how much we have to take or how much we have to pre-position. This is the number of stages we need, backdriving to how many launches we need. So that absolutely is happening and trying to inform our planning, both schedule and budget-wise.
Yeah. So I would say about 90% or more of the budget that Space Technology Mission Director has goes into what I call pull technologies, and technologies that are being pulled by mission requirements. And those requirements come from human exploration and the architecture studies in the near term, and Science Mission Directorate and what not only the Planetary Science Division wants to do in the future, but also astrophysics, heliophysics, and earth science. And so we get the requirements and we develop the technologies that will enable the capabilities that they need to enable the missions of the future in human exploration of the solar system. And then we deliver those technologies a lot of times to missions or to test beds and demonstrate them in the system, because there's technology readiness level, but there's also something called integration readiness level. And a lot of times you find, you might be TRL 6 and ready to go fly on the bench with your component or subsystem, but until you integrate them in the system and operate in the environment, you're not ready to go fly in an operational mission or in a science mission. And so that is something that, particularly with my directorate and HEOMD Advanced Exploration Systems, and then Mike Sieblum, I got to shout out to Mike. He's doing a really great job as the Science Mission Director, Chief Technologist, and making sure we understand the missions of the future across the 4 Science Mission Directorates, and we're delivering technologies that can enable not only some of the decadal survey missions maybe more affordably, but the missions that'll come in the next decadal surveys for Science Mission Directorate.
Rick, I was just going to say, do you want to add anything?
Well, no, these guys have really covered it. The only thing I would say maybe is just 2 points. One, Jim Watson, who heads up our Mars exploration program, we're here. What he would say is that we need to get out there and incrementally start building up these capabilities, actually doing them. Because that's really where you learn what it's there. And then I would say maybe a secondary theme, which I'm sure these guys would echo too, is that we can't be afraid of failure. We do our homework, we do the best we can do, and then we go out there and try it and make sure it actually works. Because you're going to learn more, even from the bad days, than you're going to learn from just sitting at a desk.
Do you want to add anything to how the robots are helping us along this path?
So, yeah, I'd love to. We have 4 major goals, like one's follow the water. If we can go back one slide, you can see this. Can we go back one slide?
I hope it's not unidirectional. If we can back up one slide. There we go.
No, the other way. Yeah, there. So this is a fleet of our current and soon-to-be missions at Mars. It's a fairly substantial fleet. A lot of it's getting pretty old, but it's been remarkable how long they've gone. We've had major goals, and you can see those down at the water, and one of which, Matt, you alluded to, is follow the water, but the other one's prepare for human exploration, and that's that big one running down at the bottom right there. And so we really view our goal, one of our major goals of these missions is to actually close what we call them strategic knowledge gaps, but these are things that we have defined within the agency that are things we really need to know to be able to safely send people there. And so knocking out those SKGs is critical, and you will see this set of missions here. And what's really cool, I'll show this chart, is you'll see the yellow ones, if I can see the colors, are international missions, and you can start seeing an amazing number of other international partners starting to move out into the Martian system now.
I want to bring up, there's so much we're not going to be able to get to today, but Rick, if you could continue for a moment. I mentioned during your intro this process that is underway that you're co-leading to select the landing site for men and women on Mars.
So we started this about 1.5 years ago. We're very excited about it. It started out as a joint STMD, HEOMD effort, and then STMD has actually participated as well. So it's really a tri-directorate thing. And we're very excited about it because, one, we have this fleet that you're seeing right here. They're getting older, and we want to actually use this fleet to help us start to narrow down the process of picking where we're going to send humans. And one thing coming out of the Evolvable Mars campaign, which is run out of the Human Spaceflight Directorate, which is that we really are trying to learn from the past. You'll see a slide here in a moment. Actually, we can go ahead and go forward to it. One more. There. We've got this idea now that we're not going, the lunar model is not what we want to do. We want to actually have a semi-permanent base. That's actually learning from McMurdo in Antarctica. Really, any other major exploration area has had essentially a transportation node where you can deliver supplies, logistics, spare parts, all the things that people will need to stay alive. And so what you're seeing here is what we call an exploration zone. In the center is a landing site. And the exploration zone is a 100-kilometer radius circle. And what we challenged in an open call is to have people propose potential exploration zones that really included diverse science and also in situ resources or feedstocks to supply that. And we were really amazed at both the number of proposals that we received as well as the quality of those proposals. And really, there are many people in this room, I bet, who actually supported that process. And it's been incredible to watch all of these teams work together to bring this together. And we are learning a ton as a result of it.
We're getting the 3-minute warning. I'm hoping Artemis and Chris are not going to be too upset if we go about 5 over, and we'll still be skipping a lot of what we had hoped to talk about up here. But Steve, if I can come back to you before we go to the audience for a few minutes of your questions for this distinguished panel. There's going to be a new president, a new administration very soon now, less than a year. Is this going to mean new priorities for space exploration? We all know NASA administrators for decades have said what we need is continuity in purpose and in funding.
Yeah, so I think what Jim discussed and is what we're doing right now to more clearly lay out our plans for human exploration of the solar system, particularly in the near term on ISS and in cislunar space. And so on ISS, it's pretty clear the things that we need to get done, and we are doing those things right now and have for many years. In cislunar space, we're going to have EM1, which is the first flight of Orion and SLS, uncrewed. EM2, which will be the first crewed flight. And then there's a succession of flights to cislunar space using Orion and SLS, most likely with a habitation module in orbit around the moon to prove out the trans-habitation capability that we need, and then prove out things like the advanced ECLS and autonomous operations and communications and navigation technology, et cetera. So it's really up to us to lay out those plans in a very concrete way to connect the dots for the administration on where we are and how do we get to humans on Mars, as well as the importance of it, right? And that's good. That's kind of what this summit is all about. Also, we need to think about in implementing civil space policy and what NASA needs to do, and Humans to Mars is a part of that, how can we maybe address other priority policy goals of a new administration? We've been an instrument of foreign policy, significant instrument of foreign policy over the history of NASA. We've been an instrument of economic policy, particularly with the current administration, education policy, et cetera. So the question is, understanding what the bigger policy objectives are, maybe the broader policy objectives are for the administration, how can what we're doing in civil place help to move the ball and address those?
Let's bring up the house lights and see if we have questions from our audience. And if you'll raise your hand, and we've got one right back here. Hi, sir, what's your name?
My name's Joseph. Let's say that we went to Mars right now. Let's say it's 2030, right? What would you rate the odds of success? Like the percentage, like 50-50, something like that?
It depends on the mission, right? We're going to Mars. Go ahead.
Yeah, no, I was going to clarify. The success rate, 50-50, is that what you're asking?
Yes, that's correct.
I hope we can do better than that.
Yeah, I would say we wouldn't be sending folks at 50-50. I think you take any risk seriously, and you're never going to buy them all down. I heard David talk about us buying down risks on station. I talked about it. You heard Steve and Rick talk about buying down risk. You're never going to buy it all down. I don't know how I would ever put odds on it.
Okay.
Because on the other hand, you can't afford to lose a crew. That's right. You know what I mean?
Yep, that's exactly the point.
Yeah, I mean, what we always want to do in all our missions is take informed risk and manage that risk down to the lowest possible level. And we do that in a variety of ways, right? We do that through simulation and modeling. We do that through ground testing. We do that through flight testing and even in-space flight testing. It's interesting, So we cannot test landing on Mars before we land on Mars with our robotic missions. Can't do it. We can't do an end-to-end system test. So we have this mantra in NASA: fly as you test and test as you fly, right? And we actually can't do that if we're going to the surface of Mars. And so, the guys at JPL and the other centers have developed this amazing, simulation capability, computer simulation capability, that's atmospheric entry, atmospheric interface to touchdown, and it has terrain model, 3D elevation models, terrain, atmospheric models, high fidelity models of all the hardware and even the software. And so, that's just what we have to do, and one of the things we have to do if we're going to go at all. So there'll be some risk, but it has to be informed, and we have to buy it down as much as we possibly can.
As Captain Kirk said, risk is our business. Let's see if we can squeeze in a couple more. Right back there, sir. Keep it very quick, please. And what's your name?
It's Mike Helton from Rockville, Maryland. I haven't heard any words of contaminating Mars. It's a very difficult situation that you have to get to Mars, but what about preserving Mars for future science exploration of the history of Mars, in particular biological history of Mars?
Planetary protection. You can't do the stuff that Mark Watney did. It's just, he should have just died.
That's right. So that's the question.
So that's a wonderful question. I'm really glad you asked it. I would say, so there's two pieces to this. If there is Martian biology, we would like to keep it segregated from Earth biology so that it makes it easier to find it. We haven't found it to date. We've found in tantalizing signatures. It may be that we may have to get humans there to actually find it, because when you have a human being with his or her amazing creativity and abilities to say, that doesn't look right, then that's probably there. So learning how to do that is going to be key. The good news is that genetic marker technologies and all these other technologies are really screaming in that area, which may make that easier. And so this is a vigorous debate that we are currently having within the agency to make sure that we don't goon up the science, but that we also, frankly, recognize that getting humans there is probably going to enable the science at a whole nother level that's never happened. And so segregating the biology is one part. The second part is protecting the crew and the people back here on this planet. We do not know whether or not a Martian biology is potentially hazardous to our crews, or they could potentially bring it all the way back to the Earth. Now, whether or not we can definitively answer that, probably not, but there's probably a due diligence component to this that we absolutely have to do. That's why, for example, when Steve referred to sample return, I personally no longer think of it as sample return from a science perspective. I think of it as integrated sample return, where we are addressing issues of not only the science that's being there, but the amazing, we want to try to understand whether or not there's biology, and two, we need to understand the toxicity of the Martian environment. Those soils have perchlorates in them, and there are a lot of other things in there that we have to learn to deal with so that we can safely know that our crews are not going to be put at harm's way when they land there, and we don't end up with a 50-50 chance that we just walked into because we didn't do our homework.
I guess we better cut it off there because I only asked for 5 extra minutes. I am so pleased to have had this opportunity, and I hope there'll be another one to ask the other questions and the others that will come up as we progress toward putting humans on Mars, which of course is what this is all about. I'm going to say up front that we're about to go into a break, but for those of you watching us online, we hope you'll stay tuned. We'll have some live content coming from here in the hall for you, but we're going to begin in just a moment with a video from Boeing, one of our sponsors here today. Please, though, first, those of you in the room, help me thank our terrific guests here that have joined us on stage, Steve, Tim, and Rick.
Thank you.
Thank you, gentlemen.
Thank you.
And if
Thanks a lot, Matt.
we can head for that video from Boeing, stay with us.
Today, somewhere out there in the world, in a classroom, somewhere between the age of 10 and 20, the person who's going to be the first person to set foot on Mars is out there, probably studying math or science. And it's really exciting to think about what that person's life will be like and how they will live after this big mission. Mars is probably in the mid-2030s. And so what we need to do now are proving ground missions that will get us ready for Mars. And it takes 6 pieces to get to Mars, and Boeing is building the SLS right now. NASA's current plan for Mars starts with SLS and Orion, the 2 pieces that get you in and out of the Earth's gravity well. If you're going to go to the moon or farther, you need a really big rocket to do that, and that's what the SLS is all about. To get you into a high orbit, and it's going to take us probably 5 or 6 SLS launches to be able to do the Mars mission. So we want to make sure that we've checked everything out and that we know that it's good to go before we actually leave for Mars. Because once we leave, we can't come back for over 2 years. And the reason for this is because it's the alignment of the planets. The way the planets revolve around the sun, it allows a window of opportunity to go from Earth to Mars basically every 2 years. Just to get to Mars, before you even land or anything, is going to take 7 or 8 months. The reality is you're going to be there for a year waiting until that window opens up to come back. And then it's going to take 7 or 8 months to come home. 2 more pieces are needed to go between Earth and Mars, a deep space tug of some kind, and we'll need a habitat. The deep space transportation is a solar electric tug with very large solar arrays, and it uses the power from the sun to drive the propulsion system, so they look like large sailing ships. And attached to the sailing ship will be a habitat where the crew will live. They'll ride in that habitat on the way to Mars, and then we'll leave the habitat in orbit when the crew goes down to the surface. And then the last 2 pieces that we'll need are the lander, and this lander will have an inflatable heat shield that will take the crew through the atmosphere and down. It'll drop that heat shield, and then the lander will land on the surface, much like the lunar lander did on the moon. And then we need a little rocket for them to get back up out of the Mars gravity well again. I think we'll be able to colonize Mars someday. It'll take time. It may take hundreds of years, but that's not unusual for humans. It's really about establishing a human foothold on the planet. It's a natural evolution of humanity to take this challenge on.